Coefficients of an interpolating polynomial. So although both the Newton and Lagrange polynomials are well suited for determining intermediate values between points, they do not provide polynomial in the conventional form. So for example, we have the conventional form in this. We do not get the polynomial in these conventional forms. So for example, in uh, the polynomial which we get is in this form, x minus 1, x, something like this. So for example, the third order polynomial we get like this, b naught into x minus x naught, x minus x naught, something like that, x minus x2, and like that. So by the Newton's formula or by the Lagrange formula. So since n plus 1 data points are required to determine n plus 1 coefficients, simultaneous linear systems of equations can be used to calculate the values of A. So for example, this may be the simultaneous linear system of equations. Okay, so we can solve this. So this is also one of the method for solving this system of equations, where x are the knowns and a are the polynomial coefficients. Okay, so uh, instead of the Newton's method and the Lagrange method, this simple direct approach can also be used. However, in this approach, normally what we get is uh, we get this matrix that is A matrix. We get that is normally an ill-conditioned matrix. So therefore, it is subject to large round of errors, and especially for higher order polynomials. So this is one of the big disadvantage for doing the interpolation or for doing the curve fitting at a higher level. So due to this reason, we use another type of interpolation, which is called as the spline interpolation as well. Also, what is the danger of using an interpolating polynomial for extrapolation? So in addition to interpolation, there is a process which is called as the extrapolation. Extrapolation is the estimation of the values outside of the range of the given values. So for example, if these 3 points are given, x0, x1, and x2, and then if we want to have the value of the function at another point, say over here towards the right of this x2, then that the choice of points over here may have some, the choice of points may have some different values of the extrapolation. So maybe the extrapolation may result may result into slightly different direction than the true curve. So therefore, we should be very careful while extrapolating the polynomials in this fashion. So we will need to have the right kind of combinations of points for the extrapolation. So for example, if once we get the curve, once we get the answer in this form, for example, in this Lagrange coefficient, so we can put any point over here to extrapolate it. But that point, the value of the function for that point may not be correct if it is outside of the range of those values which have been given to us. So there is some extra caution required for extrapolation. Okay, so the next kind of interpolation is a very special kind of interpolation, which is called as the spline interpolation. So in the spline interpolations, there are cases where polynomials can lead to erroneous results because of round-off errors and overshoot. So alternative approach is to apply the lower order polynomials to subsets of data points. So such connecting polynomials are called spline functions. Okay, so as it has been mentioned over here, that if we have large number of equations over here, the system which results is an ill-conditioned system. So that ill-conditioned system normally has the determinant value which is very low, and then that type of system, when it is solved for these unknown coefficients a1, a2, a3, etc., that results into round of errors, and due to the round of errors, the values which may be calculated, that is coefficients a1 to an, may not be very accurate. So this means that higher order polynomials, within higher order polynomials, we may have a chance of uh, getting the errors. So in order to reduce those errors, we propose the spline interpolation. So in the spline interpolation, instead of using all the data points, uh, we use a subset of data points, say 4 or 3 subsets of data points. And uh, that means, no, and then in between these different intervals of the points, we try to interpolate using the lower order polynomials. So in the lower order polynomials, we have the first order, second order, and the third order polynomials. So the most useful of them all is the third order polynomial for the spline interpolation. But of course, with this, when we say that we are using a we are not using all the subsets of the data points. There are certain limitations, and there are certain conditions. Those must be followed to set up the spline, set up the equations for the splines. And in many situations, these splines provide us some better estimate compared with the overall methods um, for finding the interpolation using all the data points, yeah, such as the Newton's method or the Lagrange's method. So this we can see in this example. Uh, in this example, we see that in this black line, we have a function. Okay, so black line has a function something like this, a constant value over here, and then there is an abrupt change, and then a constant value over here. If we uh, take 4 points on on this function and try to interpolate the values between these middle points, then we can see that the function which we will uh, this function which we will get over here will fluctuate. Okay, it will not be very accurate representation of that function. So more the number of data points which we are using over here, more will be the fluctuation. So in this case, we may not get a very accurate value for the interpolation in this case, because the function may not be representing very well uh, this function. The function because the in this case because uh, the function that is which is shown in the blue line may not be very representing the given data points over here. So in this case, a linear interpolation successive between the successive points may be the better idea. So for example, linearly interpolate between this point and this point, this point and this point, and then all the other points may give us the better results in this case. So, so there are then that means there are situations where the spline interpolation is superior to other overall interpolation methods. So spline interpolation can also be visualized as a curved spline, which if it curved physical spline. In that curved physical spline, we can fix that spline on the board of paper and then on the on a surface, and then on a drawing board, such as on a surface such as the drawing board, and then we can draw a curve with the help of that. So this is the main concept of the spline interpolation that is also used in the drafting. So there are some kinds of splines. So one kind of spline is called as the first order spline. So the first order spline is very simple. We take the first order. So for example, we consider that that spline is obtained by joining the different points with the help of lines. Okay. So for example, if we have data points, x are 3, 4.5, 7, and 9, and their corresponding fx values are given. And then we are asked that estimate the value of the function at x is equal to 5. And we want to apply the first order spline in this case. So in this case, we see that the value of x, the given value of x is between 7 and 4.5. So between these sets of data points, we assume a linear relationship. So for that linear relationship, the slope is 2.5 minus 1 divided by 7 minus 4.5. Okay, so this is the slope, 2.5 minus 1 divided by 7 minus 4.5. So there is this typing error over here, 2.5 minus 1 divided by 7 minus 4.5. So 2.5 minus 1 is 1.5, 7 minus 4.5 is 2.5. 1.5 over 2.5 is equal to 0.6. So the slope is 0.6. So we can use this slope, and then the difference between these x values, 5 and 4.5. So that is 0.5. So then we can see that then we can find the change in value from 4.5 to 5. That will be 0.6 times 5, 0.5, that will be 0.3. And 0.3 when added to 1, then that will give us the answer as 1.3. So that we can very easily get, because in this case, we are just taking the linear relationship. So similarly, for getting any interpolation value between these first 2 points, so here we have found the values between these second and the third point. In the first 2 points, if we want to find, then we can find the slope of this values, and then from this slope we can estimate the value. So that is the linear interpolation, which is rather quite simple. Okay. However, if we want to have a quadratic and the cubic simple interpolation, so there in that case we need to consider some more situations. So those situations have been represented by this general form of the curve. So for example, if we have the given data points are x1, f1, okay, x2, f2, xi, fi, xi plus 1, x fi plus 1, okay, xn minus 1, fn minus 1, fxn, and fn. That means if we have from the data point, n number of data points over here. So then we will have n minus 1 intervals in this case. So for example, if we have 3 data points, then we will have 2 intervals. Okay. So this is the interval 1, interval 2, interval n minus 1. And if we want to have the if we have say if we want to have the splines for that, then we will have n minus 1 equations for the splines in this case. Okay. So for example, first spline will be from this x1 to x2. Second spline will be from x2 to x3. So for each of these splines, we will have their equation. Okay. So those equations will be the given represented by S1, S2, S3, and up to n minus 1, etc. So this is the notation for the derivation of the splines. So first we see the case of the quadratic spline. We will see the case of the quadratic spline. So for each of the equation of the spline, for example, Fi will be the first interval, F1 will be the first interval, F2 will be the second interval, etc. We can represent the quadratic equation in terms of the ax square plus bx plus c. Okay. And then that quadratic equation will meet certain conditions, 4 conditions. And then these conditions we can see from here. Okay. So for example, for the internal points, so the internal points will be the F2 to Fn minus 1. So for these internal points, if we calculate the value of this value of F2, so this value of F2 can be calculated from the previous curve and also from the next curve as well. So the value calculated from either from the previous curve or from the next curve will be the same. So this is the first condition. Okay, so this is how it is represented over here. So for example, if we have this curve over here, this curve will give us, for this interval, we will use the value n minus 1 or I minus 1. Okay, so for example, in this case, this is the one previous term. Okay, and the another one is the one next term over here. So for these terms, if we have the data point as xi minus 1, their coefficients for the previous terms will be ai minus 1 and then bi minus 1, ci minus 1. But the data point, the common data point is xi minus 1. Similarly, for the next interval, that means for the next interval, the coefficients will be different, but the common data point will be the same, which will be I minus 1. Okay. So any data point over here, xi minus 1. So for this data point, the value that will be calculated, that will be same. So we can equate these two values and then we can get a relationship. Then the second term equation condition is the first and the last functions must pass through the endpoints. Yeah, so the first function and the last function, that will be passed through the endpoint. So endpoint may be the first point and also the last point. Okay. So if in this case, for example, if we take the first point as fx naught and the last point as fxn, so we can write 2 more equations from that. Okay. Using this equation. So just input the values of x over here. And similarly, the derivative at the interior points must be equal. Okay, so that means derivative, since the derivative selects the slope, so derivative at these exterior points must be equal. So that means the curve should be continuous at these derivative points. Okay, if we want to represent it with the help of a perfect spline, the curve should be continuous. So from here to here, it should be a continuous curve. So this means that if we take the derivative of the first curve and the derivative of the second curve at this common point, these two derivatives must be zero. So this will also provide us some data points. So for example, now in this case, the derivative of this quadratic equation will be 2a1x plus b1. Because if we take the derivative of that, it is x square term. It will be 2aix plus bix. So, and depending on these coefficients and the common data point, which is x, these two values will be the same. So this will be another condition that will be fulfilled. And the last condition will be that the last condition will be that in this case we will have to make the assumption for the shape of the curve in the endpoints. Okay, we will have to make the shape of the curve in the endpoints. So the simplest of the assumption is that we assume a linear shape of this curve from the first point and this between the first point and the second point. So when we have the linear shape over here, so this assumption will give rise to the condition that its second derivative will be zero. Because remember that in the when we take the derivative, then the second derivative shows the curvature. Okay, if there is no curvature, that means it is a straight line, and then the second derivative will be zero. So if the second derivative will be zero, then the a1 term will be zero. So for example, if we take the second derivative of this, second derivative will be 2a1. If 2a1 is zero, that means a1 will be equal to zero. So in this case, then it will provide us the last condition. Okay. So in this way, then we can write the four conditions. So looking at this example over here. So for example, we have these data points over here. Let me show you. Uh, okay, so suppose if we have here this example, fit the quadratic splines to the same data used in example 18.8. Okay, so we have these points. Okay, let me write it over here. We have these points x, f of x. So the points are 3, 4.5, 7, and what else? 3, 4.5, 7, and 9. And then 2.5, 1, 2.5, 1, right? These are the points. The last one is 0 0.5. Okay. The last one is 0 0.5. Okay, so these are the points. And then we have for the quadratic, we have this curve fi of x is equal to ai of x square plus bi of x plus ci. Okay, so this is the equation. Okay, so in order to set up the equation, so we must say that if we take the interior points, okay, interior points. So for the interior points, these are the two interior points, 4.5 and 7. So for this 4.5 point, we have this 1. Okay, the value is 1 is equal to, it will be then AI. So AI, that will be the 0.1. So for we will start I from 1. So that will be A1. Okay. And x square, it will be 4.5 square. So 4.5 square plus B1 into 4.5. Okay. And then plus C1. Okay. So we will get this curve. So 4.5 square is 20.25. So 20.25 A1 plus 4.5 B1 plus C1 is equal to 1. So we will get this first equation. Okay, 20.521 20.25 A1 plus 4.5 B1 plus C1 is equal to 1. So this equation we will get. And for the second interior point, this one, we will get, so for example, it is 2.5. So this value is 2.5, and that will be now A2 into 7 square plus B2 into 7 plus C2. Okay, so this will give us 7 square is 49 A2, because 4.5 square was 2.25 20.25, and here it will, we have 49A square plus 7 B2, 49 A2 plus 7 B2 plus C2 is equal to 2.5. So this we will get the second equation. So 49 A2 plus 7 B2 plus C2 is equal to 2.5. Okay. But additional two equations we can also get like this. So for example, if so we can get this equation also like this. So for example, 49A2 plus 7B2 plus 7 C2. Okay, so there are some two additional equations as well. So which are 20.25A2 plus 4.5B2 plus C2 is equal to 1. Okay, so we also get these two equations. So for example, this is one equation, and then we get another equation which is also same, 20.25A2 plus 4.5 B2 plus C2 is equal to 1. And similarly, we get another equation, 49 A1 plus 7 B1 plus C1 is equal to 2.5, is equal to 2.5. Okay, this one. So you can see that these equations, so for example, represent the common point. So for example, if we have this like this so we have this is the first point, and then this is the second point, and then this third point and the fourth point. So for this common point, we are calculating the value of the function from the left function and for the right function. So that common point will be 0. Okay. So for simultaneously, it will be 20.525A1 plus 4.5B1 plus C1 will equal to 1. And for A2, it will be equal to 2.5. Okay. So we will get these 4 equations. So one equation, second equation, fourth equation. Okay. For the now in this case, we can see for the um, endpoint. Okay. So for the endpoint, so for example over here, we can get also this equation. So for this is the first interval, and this is the this is for the last interval. In this case, there will be how many intervals? A1, B1, A1, B, A2, and A3. 3 intervals in this case. So the coefficients for this interval will be represented by the subscript 1. So coefficient for this interval will be represented by the subscripts 2. And the coefficients for this interval will be represented by subscripts 3. So therefore, accordingly, we will have A1, B1, C1 here, A2, B2, C2 here, A3, B3, C3 here. So for A3, we will have this point, endpoint, and then for A1, we will have this endpoint over here. So this is the equation for that. And for the last point, we have the 81 A1 because it is 9, x, the value of x is 9. So 81 plus 9 plus C3 is equal to 0.5. So 4 equations plus 2, we have 6 equations. And we will have how many unknowns? 9 unknowns, because A1, B1, C1, A2, B2, C2, A3, B3, C3, there will be 9 unknowns. So for 9 unknowns, we should have 9 equations. So up to now, we have found out 6 equations. So we need to find 3 more equations. So other 3 more equations we can find from the other 2 conditions. So for the derivatives, okay. So for the derivatives, so for example, if we take the derivative of between the first and the second interval, and then the second and the third interval, so we will get these equations. So these derivatives will be also the same, okay. So and this will give us 2 more equations, and then we will have this the last condition. We will take the value of A1 is equal to 0, because from the fourth equation we say that we will assume that we will join the first point with the second point with the straight line. So when we will join the first point with the second point with the straight line, that means the curvature of that part of the curve will be 0. So when the curvature of that part of the curve will be 0, its second derivative will be 0. So if the second derivative is 0, then that means A1 will be equal to 0. So in that case, this is our 9th equation, but we can simplify it by putting the A1 is equal to 0. So in the end, we will get an 8 by 8 matrix. And then this 8 by 8 matrix we can write in terms of the B1, C1, and then A2, B2, C2, and then A3, B3, C3. Because A1 was 0, so we have eliminated it from here. And then corresponding to B1, C1, we can write it. So for example, if it is B1, C1, that means how we can write it. So B1, C1, because now A1 is equal to 0. So A1 will go out from this equation. So it will be 4.5 B1, and then 1 C1, and then 0, 0, 0, and then 1. So here we have written it like this: 4.51. These corresponds to B1 and C1, and then of course A2, B2, C2 are all 0 for this first row. And then here we can get that we are getting these coefficients. So this is an 8 by 8 equation which can be solved by MATLAB or by any other approach you know, for example, in Excel as well. So when you solve it, so then we will get these values. A1 is equal to 0, and B1 is equal to -1, C1 is equal to 5.5, and likewise we get these values. Okay, so these values now we can input into the equations, the general form of the equations. Then we can get the three equations. Okay, so first equation is for the first interval, the second equation is for the second interval between 4.5 and 7, and the third equation is for the interval between 7 and 9. So now if we want to interpolate the value at x is equal to 5, we can use the second equation, and then we can put the value x is equal to 5 into that equation, and this will give us an answer which is equal to 0.66. So in this case, uh, the spline value will give us this value. So here we can see that the second order spline will go like this. However, the second order spline is uh, you can see that it is giving us a little bit of fluctuation as well. So for example, beyond this point, the curve is offshooting towards one side, and then after this over here we can see that beyond this point is the curve is also offshooting towards downward. So in this case we can see that the second order spline is not giving us a very accurate result. So for example, the total fit of the spline is shown in this figure 18.16b. So notice that there are two shortcomings that detract from the fit in. The straight line protecting the first 2 points, and the spline for the last interval seems to swing too high. So it is swinging too high actually. So therefore this second order spline, which is shown over here, due to a large swing, it does not seem to give us a very good answers. So therefore we can try the third order spline. Okay. So the formula for the third order spline it can also be obtained in a similar manner, but in the book there is a but that if we use that formula in a similar manner, then we will use, for example, if we have been given like 4 points, and then in those situations we will have to solve like 16 equations for 4 points, which will be a tremendous effort. However, many of these values in those equations will be 0. And then there is a slightly simpler way for solving those equations. And those simpler ways will use like n minus 1 condition. So for example, if we will have say 4 data points, then we will only need to solve, instead of 16, we will only need to solve like 3 equations, okay, to get the answers. So the simple formula, which is actually not very simple in this location, is given by this. Okay, so it's very lengthy formula to remember. So therefore, this formula, whenever we'll use, whenever you want to use this formula should be handy and in front of you. So if it is f I of x is equal to f double prime of I x minus I xi minus 1 and f double prime xi. So in this formula to use, we have unknown value of f double prime, because initially we will have the values of x and fx, but this formula use the f double prime of x. So this f double prime of x can be calculated by another equation. This is the second one. Okay, so this is the first equation which I just showed over here, and this is the second equation. So using this equation and the conditions, we can calculate the values of fx, okay, by two equations. F double x, f double prime of x can be calculated by this second equation, which can be input into this first equation to find the value of the f of x. Okay, so the overall um, length of these two equations is quite long. So I will not go into the details of that. And then, however, in the book, it has been derived, but we will not go to the derivation of these two equations over here. So just see the example for the third order spline. So in this third order spline, we have the same data as before: 3, 4.5, 7, and 9, and then like that. From these data points, we can see that x naught is 3, x1 is 4.5, and x2 is equal to 7, and then their corresponding fx values. So using these values, we can input these values. Okay, we can input these values into this second equation. Okay, and then we will get an equation in terms of we can get an equation in terms of f double prime of 3 and then f double prime of f. So because of the natural spline condition, f double prime of 3 will be equal to 0, because for the end condition. So we can put f double prime of 3 is equal to 0 over here. In the end condition, we will assume that in natural spline. So the curvature will be 0. Okay, there will be no curvature, straight line. So if the curvature is 0, then double prime will be 0 over here. So this a set of first 3 points will give us these two conditions, where there are two unknowns, f double prime of 4.5 and f double prime of 7. Okay, so we will get one equation from here, and then the second equation we will get from the second to the fourth point, these sets. That means 4.5, 7, and 9. So this is the second set of points. So this, from the second set of point, we will get another equation, which will be f double prime of 4.5 and f double prime of 7. So these are the two unknowns. So solving these two equations, we will get the values. Yeah, we will get the values of f double prime of 4.5 and f double prime of 7. And then these values of the f double prime of 4.5 and f double prime of 7 will be substituted into this first equation. All the other values are known in the first equation. And then in this way, then we can get the first equation, which will be in this form, So this first equation will be for the first set of data points. That means for the first interval, that means for this interval. Okay, this first equation will be for this interval. So this process will be repeated for the second interval and also for the third interval to get the equations. Okay, so similarly, then for the when we repeat the process for the second interval, we will get this equation. We will repeat the process for the third interval. We will get this equation. So what you have to do is you have to find these f double prime 4.5 and f double prime 7. Once we have found it, so we can iteratively apply these equations. Okay, so and then we can get these equations. Okay, so the second of this equation is for interval 4.5 and 7.5. So if we want to interpolate the values between 4.5 and 7.5, so we will put the value of x is equal to 5 into this second equation. And then here we will find the value of the interpolated value of 1.1 over here. So this will be the answer for the interpolated value. And as we can see that in this chart is the cubic spline has been shown over here. So in this cubic spline, we will see that the curve which we have found over here, uh, which is represented by this solid line, is not offshooting too much. It's not swinging too much over here. So this seems to be a good fit of the data, and that we can see it from the interpolating cubic as well. So if we find the interpolating cubic over here, and then this cubic spline over here, this interpolating cubic and the cubic spline seems to fit each other quite well. So therefore, the cubic spline gives us the best fit of the data in this case, and the results are more reliable with the cubic spline. Okay, so this example then results into the conclusion that the cubic splines uh, are much better to use compared with the quadratic splines, and to some extent the linear splines as well. Okay, so that's why in MATLAB we have only the function for the cubic spline. So cubic spline is the most commonly used, and it is the most accurate type of spline. Okay, so the next is the one last topic is the multi-dimensional interpolation. So it is basically nothing much new in this case. It is just the linear interpolation. So for example, if we have a data point which is x1, y1, and another data point in 2 dimensions, which is x1, y2, and another data point which will be x2, y1, and then x2, y2. Okay, so if we have these 4 data points, which are basically the 4 corners of these planes, then we want to find this value of the function at any point in between these plane. So then we can do this with the help of linear interpolation. Okay, so this is called as the linear interpolation. So in this case, first we will interpolate from x1 to xi at the level of y1, and then we interpolate from the also from x1 and x2 to at the level of y2. So from these 2 points, then we will interpolate between the values of y. So we have to apply the linear interpolation 3 times. Okay. There are actually some formulas for that as well, but it is very simple in the concept. So first you interpolate between 2 x points, so 2 times interpolation, and then those 2 obtained points, then you will interpolate between these 2 points as well. So as an example, so in that situation, we don't have to look at or memorize even those formulas as well. So for example, if we have these data points 2, 1, 60 and 57.5, and 2, 6, 55 and 70. So what you can do is you can first interpolate between 60 and 57.5 for the linear interpolation. Then you can interpolate between 55 and 70 with the linear interpolation. And then since we have obtained these 2 points, then we can interpolate between these 2 points as well. And then you can get the final answer over here. Or otherwise, you can just input these values which will be into this very long given formula, which is not very easy to remember. So both of the equations, both of the approaches can be used. But for me, I think for this bilinear interpolation, I will be using first I will interpolate between these 2 points. Second, interpolate between T26 and T96. Okay, and then there will be one more interpolation which I will perform over here without remembering the formula. Then you can interpolate it. So for example, here I have done in Excel this kind of interpolation. Okay. Yeah, the time is actually over actually, so that's why I could not explain it very much today. But anyway, it should be understandable to you. All right, so